All right. Here we go. Day 2 of section 2.2. Okay. Remember, this is what we did on day 1. We worked on the leading coefficient test that helps us determine the end behaviors. Hopefully that went well. Don't forget to self-assess and make sure you're on track there with those rules. We also work on finding real zeros, and we worked with a lot of characteristics of polynomial functions, which we'll review in just a second. All right, because there's one more example I'm going to show you in today's notes that still relates to this learning target. Okay, here's what I want you to do with this last learning target. We don't use the intermediate value theorem, so I want you to cross that out for me, okay, in your notes, and I want you to replace it with one that we will be using. It states, given the degree and zeros, I can write a polynomial function. Okay, pause the video and write that in there, okay? All right, so piggybacking off what we went over on day 1, remember all these characteristics we went over on zeros of polynomials. Max number of zeros, I'm just going to go quick. X-intercepts are related to the zeros, right? Wherever it's a way you can check your answer. Whatever zeros you get by hand, you can check the graph to see if they match up with the x-intercepts. All right, we also went over multiplicity concepts. It's the number of times a root happens or a zero happens, and then the max number of turning points is degree minus 1. Okay, so let's take a look at example 11. This is page 14 of your notes. Example 11, page 14. Why don't you get there right now? Okay. All right, so remember the directions for this problem. Flip over and take a look here. We're going to find all the zeros of the polynomial function first. Once we have the zeros, we're going to have to determine the multiplicity, and we're also going to identify the max number of turning points. Okay. This last step, the OTI the other day, it was labeled as Part D. This is optional. You can use a graphing utility to verify some of these things. Verify the max number of turning points, verify your zeros and the multiplicity. And remember, if it has odd multiplicity, you can check to make sure that it crosses at that spot. Okay, so there's the directions. And here's 11. Okay, so 11. Now, for most of these, once we set it equal to 0 to start finding our zeros, we have to use our factoring strategies. Okay, so here's what I put in parentheses. You may want to add this as well. Look to factor by grouping. That is, you should look to factor by grouping when you're presented with 4 terms. Chances are it's going to be factorable this way. Okay, so to factor by grouping, remember we take the first group and we try to take the GCF out of that group. And in this case, we can take an x squared out. Okay, go ahead and follow along and write that down. And remember, you just kind of fill in the blank. X squared times x is x cubed. X squared times positive 2. It checks out. Now I move on to the next group. Whatever sign is in front of that next group, you need to transfer down. Okay, and I can take a 4 out of both of these. So I put the 4 out front, and once again, kind of check as we go. Negative 4 times x is minus 4x. Negative 4 times positive 2 is negative 8. Okay, so if it is factorable, this should be a common factor now. So now x plus 2 kind of comes out of both of these. And so it looks like this. 0 equals x plus 2 times, now when I take that out, what am I left with? X squared minus 4. Okay, now I can continue to factor this. So I'm going to continue to break this down. Remember, this is what we call difference of 2 squares. A little side note here, remember anytime it's a squared minus b squared, we can quickly factor it to a plus b times a minus b. So that's what I'm going to do here. The x plus 2 is all set, but this one is going to be x plus 2 times x minus 2. Okay. All right, and we can write this as x plus 2 quantity squared. It's kind of up to you. I don't care. I mean, we should realize that this 0, it happens twice, or has a multiplicity of 2. All right, but I'm going to go ahead and take it one step further and write that as x plus 2 quantity squared, and then x minus 2 is just to the first power. All right, so now I can name my zeros and I can name the multiplicity. So my zeros are, this one, if I set it equal to 0 and then solve it, we subtract 2. So I get negative 2 with multiplicity of 2. Okay, so when I check this on the graphing calculator, I should see it touch the x-axis at -2. The other one, when I say x minus 2 equal to 0 and add 2 to both sides, we get positive 2 with multiplicity of 1. Okay. Last thing the directions were asking for was the max number of turning points. So the max number of turning points is always given by the degree minus 1. So since this is third degree function, we take 1 away from that to say that it's 2. So max number of turning points is 2. There's the solutions to that problem. Okay. In today's OTI, I think you have 2 kind of like this. They're mixed in. You got to know which strategies to use. So if we look at all our strategies, we just got to kind of react. So we had grouping method. Number 9, right away we could take an x squared out. So we use GCF and then factored that quadratic into 2 more. What do we have on 7 and 8? 7 was square root method, or we could have used difference of squares, right? This is a squared minus b squared. And then this one was already they already started factoring it for us. So you just got to react to what you're given, okay? All right, last type of problem. We're going to move on to this last learning target now. Given the degree in zeros, I can write a polynomial function. Okay, so the directions look like this. Find a polynomial function, so that's where we're going to write it, of degree n that has the given zeros. There are many correct answers. I'll show you what that means when we're done or near the tail end of this first example. All right, now we're going to need something that's actually formally presented in section 2.3, but we kind of need it now. So I want you to write this little version of factor theorem. This really shouldn't get in the way of our work if you nestle it over here off to the side, okay? So go ahead, write this down. It states this, factor theorem. If k is a 0, then x minus k is a factor. Okay, pause and write that down. Okay, now it's pretty fundamental. Think about it. If we go back to these last 2 problems as examples to talk about the factor theorem, for example, 2 was a 0, right? So if I go back a step, what was the factor? How did I get 2? It was because x minus 2 was a factor. And when I set that equal to 0, we added 2 to both sides, so we got a 0, 2. So if 2 is a 0, then x minus 2 is a factor. Works with -10 as well, right? If negative 10 is a 0, then x minus -10 or x plus 10 is a factor, okay? So that's how we're going to start writing this function. I'm given a 0 of -3. So we're going to say, all right, the function is going to be equal to this, though. X minus a -3 must be a factor. It does say degree 2. So something else we talked about on day 1 was the max number of zeros is going to be equal to the degree of the polynomial. So we're expecting 2 zeros here, but they only gave me 1 0. Okay, so that means we're left with assuming that this 0 has multiplicity 2. Okay, so I should probably write that in somewhere. Let's write it right here. We must assume that -3 has multiplicity of 2 in order to have a degree of 2 and have 2 zeros. Okay, whatever the degree is, we should have that many zeros. So the next one is degree 3. We have 3 zeros. Okay. All right, so x minus -3, and then I got to do it again. X minus -3. Okay, so yeah, we can write that as x plus 3. I'm just trying to break it down step by step right now. So we're going to write this as x plus 3 times x plus 3, and we're going to write this or find it. And I want you to multiply it out. It's kind of going backwards, right? So these are my factors. Multiply it and then get this for your answer. That's what we're doing. Okay, we should be pretty good at these steps. Multiply, first times first, outside. 3x. Inside, we get 3x. In the last two terms, we get 9. So my function is x squared plus 6x plus 9. Now, here's why they say there are many correct answers. Right now, my answer is assuming an a value of 1. Okay, but this is another possibility. It is possible for a to be 2 and still have the same zeros. Let me show you what I mean. You don't have to write this part down. Just watch. So if a is 2, I'm going to do 2 times x squared plus 6x plus 9. And I get this new function. So 2x squared, multiply 2 here to get 12x. And then 2 times the 9 gives me 18. Okay, now what do these two functions have in common? What they have in common is they have the same zeros. But by multiplying by 2, it just kind of stretches the graph out if we were to analyze that. And we don't have to. All I'm trying to show you is that there's a lot of possibilities. So this is a correct answer, but this is a correct answer. And if you chose an a value of 3, if you chose an a value of 3.5, and so on, right? The possibilities are endless. Okay, I don't expect that you don't have to do this step. I'm just addressing the fact that there are many correct answers. All right, most of you will just stop with an a value of 1. I would too. I don't blame you, and just make that your answer. Okay, so when you check your answers in the back, sometimes they may have this, like that answer times, and they put a sub n out here saying you got all kinds of possibilities. All right. Okay, so for 13, your turn. I want you to set up your factors. Okay. Actually, you know what? Take a moment. Why don't you pause? Try to set up your factors. Why don't you take about 30 seconds to do that. Then unpause. I'll go over that, and then I'll let you multiply it out. Okay, so go ahead and do the first step for 13. All right, so factor theorem. So x minus a negative 1 is going to be x plus 1. X minus 2, x minus 4. Do the number of factors and zeros match up to the degree? Yes, they do. So we're all set. They all have multiplicity of 1. Now we start multiplying this. Here's my next advice here for the next step. You've got 3 binomials. Just choose 2 of them to start multiplying. It's up to you which ones. Okay. For your feedback, I'm going to multiply these 2. So once you multiply these out, then that result, multiply it by x minus 4. Okay. Pause and give it a go. Okay, here we go. Multiply those. We get x squared minus x minus 2. How do I multiply these together? Here's what you should do. Just take this x and distribute that through. So x times x, x cubed. X times x, x squared. X times 2, minus 2x. Now that I'm done with that, I take negative 4 and I do the same thing. Negative 4 times x squared, and so on. Keep distributing, okay? And collect like terms, and that's what you get, okay? Pause and rewatch if you need to. But let's go ahead and take a look at the last example. All right, this one, I'm given degree 3, so we should have 3 zeros, but I only have 2 zeros. So here's what we're left to assume. Write this down. One of these zeros must have a multiplicity of 2. Okay, so here's what you can assume. Either x equals negative 2 happens twice and x equals 1 occurs once, or x equals 1 occurs twice and we have x equals negative 2. It doesn't matter. If this is a problem on a test, there's going to be two correct answers and you can choose. All right, so why don't you go ahead and pause and you try one. Either try this one or that one. I have both solutions, and then we'll return and go over the feedback. Okay, pause now and give it a shot. And here they are. Okay, once again, I multiplied the first 2 binomials together, then distributed. Same thing over here. Both of these are acceptable answers. Okay, I just kept a as 1. Used a as 2 or 3 or something like that. That's fine too. Okay, so part of your assignment will be in the, most of your assignment's probably going to be in your notes. Okay, there's some additional practice to follow. Have a good day.